It didn't enter like a comet. And it didn't follow the path we expected. By the time 3I Atlas neared Jupiter's influence, it had already rewritten the rules of interstellar motion. Most celestial bodies caught in Jupiter's gravity well show predictable behaviour: a tightening arc, an accelerating spiral, or a slingshot deflection. But this object behaved differently. Not violently, not erratically, just quietly wrong. Jupiter exerts the strongest gravitational pull of any planet in the solar system. Even distant interactions with its field are enough to alter asteroid belts, redirect comets, and create permanent moons from captured objects. If 3I Atlas were a natural body, it should have been dragged into a spiral, flung outward in a textbook assist, or torn apart by tidal stress depending on its speed and composition. But instead, telescopes tracking it noticed something unusual in the final approach phase. The object slowed, not abruptly, just subtly. Its velocity curve, plotted over successive days, began to show signs of deliberate deceleration. The change was so smooth that it initially went unnoticed, attributed to minor errors in measurement or fluctuations in solar wind drag. But by the time it reached the outer edge of Jupiter's magnetosphere, the data was too consistent to ignore. This wasn't noise, it was intent. Ground-based observatories in Chile and Hawaii, along with deep space telescopes and the Juno probe, confirmed a series of micro-adjustments to the object's trajectory. These weren't typical gravitational perturbations, they occurred in patterns, at intervals that didn't match known resonance harmonics. Every vector correction was subtle, as though the object wasn't being pulled, but was choosing. Some compared the maneuvering to aerobraking, the technique spacecraft used to skim atmospheres and reduce speed. But 3I Atlas wasn't using gas thrusters or deploying physical sails. There were no visible outgassing events, no coma expansion, no tail eruptions that could explain the motion. It was as if the object adjusted itself by means we couldn't detect, redirecting its own centre of mass, or interacting with local forces in a way we don't yet model. The first major inflection point occurred just beyond Jupiter's Hill sphere, where gravitational dominance begins. Standard simulations predicted a slingshot path, a wide, elegant arc curving outward toward the solar system's edge. But 3I Atlas deviated from the model by half a degree, then another. The angle shift wasn't large in spatial terms, but in cosmic mechanics, even a fraction of a degree translates to millions of kilometers over time. Analysts at ESA and NASA independently ran recalculations. The new path suggested not an escape vector, but a rendezvous curve, one that would bring 3I Atlas into near-parallel alignment with Jupiter's rotational equator. That's not random. That's targeting. The curvature wasn't natural, nor was the pacing. Every update to the trajectory data revealed a pattern too smooth to be coincidence. Comets don't adjust mid-course without visible interaction. They drift, wobble, spin. They fragment under pressure. But this one didn't flinch. It bent, softly, strategically. And then came the spin down. In the final approach hours, 3I Atlas's rotation rate, previously negligible, dropped even further. The object became almost inertially flat, like a spacecraft entering a stabilization phase before atmospheric entry. This has no analogue in natural comet behavior. Passive bodies don't de-spin before impact, but engineered ones do. When the final entry vector was calculated, scientists expected turbulence, disruption, and jetting. Instead, the object lowered itself into Jupiter's upper atmosphere along a path that matched, within margin, what we'd expect from a guided orbital skim. Not a dive, not a crash, a brush. And with that, the silence began, not from the object, but from the data. To understand what happened next, you first have to understand what Jupiter is, not just in size or appearance, but in function. Jupiter is not a planet, it's a gatekeeper, a regulator. A magnetic wall that defines the outer boundary of terrestrial stability in our solar system, and anything that crosses into its field gets judged. At more than 300 times the mass of Earth, Jupiter's gravitational influence is vast. Its sphere of control extends so far that it routinely plucks asteroids from the Kuiper belt, flings long-period comets into interstellar space, or swallows up wandering fragments before they reach the inner planets. It doesn't just orbit the Sun, it shapes the paths of everything around it. And yet, For all its mass, Jupiter is not solid. There's no surface to impact, no crust to shatter against. What it offers instead is something far more dangerous, a layered storm of gas, heat, and electromagnetic chaos. Its atmosphere, composed primarily of hydrogen and helium, is dense enough to crush steel the deeper you go. The temperature gradient is steep, the pressure is relentless, and buried within all of it is a magnetic field 14 times stronger than Earth's, a swirling maelstrom of charged particles and invisible forces. That's what makes Jupiter different. Not just big, not just violent, but active. So when 3I Atlas approached it, scientists watched with more than curiosity. Because for the first time since this object had entered the solar system, we were about to see it tested against something dynamic, not passive like the vacuum of space or distant radiation bands. Jupiter was going to respond. And if 3I Atlas was truly natural, we'd find out very quickly. We've seen what happens to objects that get too close. In 1994, fragments of comet Shoemaker-Levy 9 slammed into Jupiter's atmosphere after being torn apart by tidal forces. The result was catastrophic. Visible scars in the gas giant's clouds that lingered for months. A reminder that even cosmic wanderers don't walk away untouched. Even massive ice balls, kilometers wide, break apart under Jupiter's grip. But 3I Atlas wasn't behaving like Shoemaker-Levy. It didn't break. It didn't fragment. It didn't heat up in the expected way. And that's when scientists started asking a different kind of question. Not will it survive, but what does survival even look like for something like this? Because Jupiter is more than an obstacle. It's a lab. A pressure cooker of physics that strips away assumptions. The moment 3I Atlas entered Jupiter's magnetosphere, it stopped being just a visitor. It became a subject of real-time experimentation, charged particle density, plasma shearing, turbulent field reconnection. These are not abstract terms. They're real environmental conditions, forces that interact with matter and movement. Any object passing through is scanned, tested, and pulled at from all sides. It's not enough to resist gravity. You have to survive data exposure, light distortion, and magnetic deformation. And yet 3I Atlas passed through that field with eerie calm. The surrounding clouds barely stirred. No tail separation, no ion burst, no thermal bloom, just movement. Clean, uninterrupted, and anomalously smooth. Jupiter should have challenged it. Instead, it revealed it. Whatever 3I Atlas is, it was built, or born, for encounters like this. And whether it was collecting data, extracting energy, or testing its own systems, it didn't behave like an object under stress. It behaved like an object doing its job, and Jupiter, for all its power, became just another step, a test, a mirror, one it passed without blinking. This wasn't an impact. There was no explosion, no fiery burst, no atmospheric plume that rose into the clouds. Instead, it was a skim. 3I Atlas didn't crash into Jupiter. It brushed it, softly, precisely, and with a level of control that made every model fall silent. The expected sequence was clear. An object from interstellar space, even a loosely bound chunk of ice and rock, should spiral inward and burn. Jupiter's upper atmosphere isn't forgiving. It begins as a haze of hydrogen and helium, but within seconds of entry the pressure climbs. Within minutes, so does the heat. Most bodies disintegrate before they even reach the lower cloud layers. The mechanical stress alone, from the changing density, from the friction, from the rapid acceleration, is enough to shear small objects apart. But this one didn't shear, it slowed. High-resolution infrared data from the Juno probe detected something that had never been recorded before during a Jovian encounter, a stable thermal signature, skimming just above the visible cloud deck, maintaining altitude for nearly 24 minutes, and then pulling up. Let that sit for a moment. No comet does that. No natural body, not even the most solid of asteroids, glides across the top of a gas giant's atmosphere like a stone across a lake and comes out whole. But 3I Atlas did. The first signs of the skim came not from visual imagery, but from turbulence readings. As it approached the limb of Jupiter's equatorial band, a subtle horizontal wave emerged. Wind velocity shifted, cloud forms distorted, not vertically, but sideways, as if something had displaced the upper layers without cutting through them. It was as though the object created a corridor. The spectrometer arrays from Earth-based telescopes confirmed a reflection anomaly that passed through the band at an angle inconsistent with pure descent. In simpler terms, the object wasn't falling, it was navigating. The curvature of its descent flattened just as it should have steepened, and the trajectory matched what spacecraft designers call a lift-generating skim, a technique typically reserved for aerobraking maneuvers around solid planets. Jupiter doesn't have a solid surface, but it does have a defined atmospheric gradient, and somehow, Thrikardry. Atlas knew exactly where to enter to generate the lift it needed to swing around the planet without losing structural integrity. The temperatures recorded along the path were equally bizarre. As it passed through atmospheric layers exceeding 600 Kelvin, the object's own infrared signature rose only slightly, before stabilizing. That implies thermal regulation, not shielding, not ablation, but active heat management, like something controlling how much energy to absorb and when. And then there was the color shift. In the moments immediately following the skim, ground-based optical sensors picked up a faint blue trail, a glowing arc that traced the object's motion. It didn't behave like ionized gas. It didn't dissipate in the normal fashion. It held for nearly 90 seconds, then faded. The glow was tightly aligned to the object's vector, as if 3i Atlas had emitted a signature, intentionally or not, in response to the atmospheric contact. Some scientists speculated it was a plasma echo, residual charged particles from the magnetic pressure. Others suggested a self-contained electromagnetic field, briefly destabilized by the density gradient. But no one could explain why it curved so perfectly, or why it lingered. Because that curve wasn't chaos, it was orchestration. And in that orchestration, the object didn't just pass by. It performed something, a maneuver, a test, a sample, a skim across a giant that should have destroyed it, but instead revealed it. Jupiter was never the target. It was the touch point. It should have come out damaged, scorched, cracked, fragmented. But when 3i Atlas emerged from its atmospheric skim over Jupiter, it wasn't broken. It was unchanged. This is the part that challenges the deepest assumptions in space physics. Because re-entry, at any level of a gas giant's atmosphere, is not survivable for fragile structures, not without damage, not without signature heat spikes, erosion, or trailing debris. Yet the object didn't exhibit any of those. No thermal flare, no radiative bloom, no signs of sublimated layers, just stability. The expected temperature during entry into Jupiter's upper cloud bands ranges from 600 to 1000 Kelvin, hot enough to instantly vaporize exposed ices and fracture any unreinforced rock. Add to that the immense friction from plowing through hydrogen-rich currents, moving at hundreds of kilometers per hour. And you get a recipe for absolute destruction. A comet would disintegrate, an asteroid would break apart, even metal-rich meteorites would show signs of thermal stress. But 3i Atlas didn't even flicker. Infrared readings taken by multiple observatories, from Juno, from Earth-based scopes, and from orbiting infrared satellites, all returned the same result. The object's surface temperature remained within an extremely narrow band before, during, and after the skim. No sharp increase, no sign of internal heating. It behaved like it was rejecting heat, or worse, like it was never absorbing it in the first place. This raises a difficult question. How? Standard cometry models account for ice layers, dust crusts, and volatile gas trapped beneath surfaces. All of these react violently to rapid heating, especially during close planetary encounters. But if 3i Atlas is truly interstellar, its surface should have been exposed to eons of radiation. Hardened, yes, but still layered with materials that vaporize under stress. Instead, we saw an object that maintained structural coherence, thermal balance, and vector stability through one of the harshest natural environments in the solar system. The data doesn't point to a shielded core or a cometary crust. It points to something more radical, a material or system of materials that actively manages thermal load. Not passive resistance, active regulation. One theory emerged from atmospheric physicists in Japan. They proposed that the object may possess a layered shell composed of carbon-rich composites, perhaps analogous to aerogels or metamaterials, able to reflect infrared radiation and minimize conductive transfer. In short, a thermal skin, Not necessarily artificial, but certainly exotic. Others took it further. A group at the Max Planck Institute ran simulations based on materials with variable emissivity, surfaces that changed their reflective or absorptive properties based on temperature. They found that if 3I Atlas's outer layer had even a fraction of this behaviour, it could theoretically maintain core temperature under the stress of re-entry, assuming its rotation remained minimal and its exposure angle was precise, and it was. The spin data from just before and after the skim showed negligible rotation, almost as if the object had deliberately flattened its motion to minimise drag and surface heating. That kind of behaviour doesn't emerge from randomness. It suggests awareness, not conscious perhaps, but algorithmic, adaptive. The final piece came from a Canadian observatory scanning for residual ion trails. It detected nothing. No cloud of particles, no stream of escaping volatiles. The re-entry left no scar, on the object or in the surrounding atmosphere. The absence became the signature, because nature leaves evidence when it struggles. When something burns, breaks, or melts, it leaves a trace. But this didn't. It slipped in and came out clean. Most people think of Jupiter as a planet of gas and gravity, a swirling mass of pressure systems and storm bands. But what surrounds it is far stranger and far more powerful. A magnetic field so massive that it forms a second invisible planet, one made entirely of force. Jupiter's magnetosphere is the largest structure in the solar system, stretching several million kilometers into space. If we could see it with our eyes, it would dwarf the Sun. This is not just a passive field. It's a fortress of charged particles, plasma waves, and electromagnetic interference. Anything that crosses its boundary isn't just entering Jupiter's orbit. It's stepping into a system of tension, compression, and response. So when 3I Atlas approached that boundary, scientists prepared for a show. The first sensors to react weren't optical. They were magnetometers, precision instruments aboard the Juno spacecraft, orbiting within Jupiter's field. At exactly 0402 UTC, they recorded a spike, not random noise, a pulse, a clean, rhythmic burst of magnetic interference that didn't match solar background radiation or the planet's known periodic cycles. It repeated every 63 seconds for over half an hour. At first, mission engineers thought it might be a local event, a wave echo or an interaction with the solar wind. But ground-based observatories reported the same thing. Arrays in New Mexico and Australia, separated by half the globe, confirmed identical readings in the ultra-low frequency band. A pattern was forming, and it was centered on the vector of 3I Atlas. The pulse wasn't loud, it wasn't aggressive, it was just deliberate, like a radar ping, like something mapping the field around it as it moved through. This is where theories began to diverge. One group suggested it was a magnetic wake, the result of an object disrupting the ambient plasma with an unusually conductive surface. That might explain the pulses as byproducts of field distortion, but the spacing was too regular. Nature creates turbulence, not rhythm. Another theory, more unsettling, came from a team at MIT. They proposed that 3I Atlas wasn't just reacting to the field, it was using it. Not just shielding itself, but manipulating local densities, tuning its motion, surfing the gradient. Think of it like this. If a bird flies through wind, it doesn't just push against the air, it reads it, adjusts to it, rides it. What if 3I Atlas was doing the same thing with magnetic force? Supporting that idea was a second anomaly. In the hours following the first pulse detection, the Jovian plasma torus, a thick belt of charged particles originating from the volcanic moon Io, showed a localized deformation, a dent, a compression, not from Io itself, but from something that had moved through the region with coherence and mass. 3I Atlas didn't just glide through Jupiter's field, it left a path, a trail of bent force lines, not visible, but measurable, like a footprint on a pressure plate. No natural comet has ever done this. Comets scatter particles, they shed dust, they cause local interference, but never symmetrical, never sustained, never aligned with magnetic geometry. This was different. It wasn't a disruption, it was a conversation. The field changed shape around the object, not violently but smoothly, like something shifting to accommodate a guest that already understood the rules. And when the pulses stopped, they didn't fade, they concluded, 63 seconds, again and again, and then silence, as if a handshake had ended, and the real work could begin. Every comet has a tail. It's the signature behavior we've come to expect. A shimmering streak of gas, ice, and dust particles blown away from the object's core by the pressure of sunlight and the solar wind. The tail always tells a story. It forms as a comet approaches heat, it grows, it curves, and eventually it detaches. It fades into space, that's how it ends. But with 3I Atlas, that story was rewritten. Because this tail didn't fade, it moved. And it moved with the object, not trailing behind like smoke, but shifting around it like a cloak that understood its owner. Let's go back to the moment just after the atmospheric skim. Most astronomers watching the object expected the standard signs of tail dispersion, material trailing, lengthening, expanding outward, and slowly dissolving as the object accelerated away from Jupiter's gravity. But that isn't what happened. Instead, high-contrast optical readings from ESA's solar orbiter revealed something few had ever seen before, a tail that began to reposition. At first, it lingered behind 3I Atlas in traditional alignment, as expected. But within 40 minutes of the Jupiter skim, the dust structure began to deform, not due to solar wind, but seemingly in response to the object's own maneuvering. Spectral imaging captured a slow reorganization of the material, coalescing into a thinner, more focused stream that repositioned itself forward of the nucleus, then back again. This wasn't behavior caused by solar radiation pressure. It was behavior that followed intent. Comet tails, by their nature, are reactive. They scatter depending on the object's direction, the angle of sunlight, the influence of magnetic fields. But this tail showed none of the drift patterns we associate with traditional outgassing. Instead, the entire formation appeared bound to the object, maintaining a fixed spatial relationship regardless of external conditions. In simpler terms, it wasn't a tail, it was a field. Scientists at the University of Arizona working with coronagraph data suggested something astonishing, that the tail may not be composed purely of gas and dust, but of magnetically bound particulates. If true, it implies an interaction between the object and surrounding plasma far more complex than cometary sublimation. The movement of the tail relative to the object also hinted at containment. When the leading edge of the tail passed in front of the nucleus, it maintained cohesion, not dispersing into space as dust clouds typically do, but holding shape, like something under tension. A leading theory proposed that the material was trapped inside a weak electromagnetic shell, one potentially generated by the object itself, or triggered by its interaction with Jupiter's massive magnetic belt. Another group posited something bolder, that the tail might not even be a byproduct of the object's composition, but a system, a component, perhaps part of a propulsion mechanism, a solar sail array, or a shielding envelope designed to interact with magnetic environments like Jupiter's. Whatever its function, the tail remained with 3I Atlas long past the point where it should have faded. Nearly 6 hours after the encounter, it was still visible, still coherent, still responding to the object's vector shifts like a flexible appendage. Not awake, and that's what changed the language scientists used to describe it. No longer debris, no longer exhaust. Now it became something else entirely, not what the object left behind, but what it brought with it, and kept. Energy doesn't just move through space, it changes hands. When 3I Atlas passed through Jupiter's magnetic environment, the transfer wasn't subtle, it was measured, it was structured, and it didn't come from the object, it came from the planet. Most encounters between comets and planets result in loss. The comet sheds mass, it leaves particles, its volatiles get stripped, its surface eroded, and it exits lighter, often fractured. But this time, something inverted. Jupiter lost something. Spectral data from the Solar and Heliospheric Observatory, SOHO, recorded a short-lived reduction in ion density along the path of 3I Atlas's skim. Specifically, a depletion of hydrogen ions or protons in the upper Jovian atmosphere, just in the region where the object passed. This was no small fluctuation. Over a window of 18 minutes, proton concentrations dropped by nearly 4%, then returned to normal as if nothing had occurred. What could cause a selective ion dip in Jupiter's own upper layers? At first, scientists looked for electromagnetic storms, solar flares, internal disruptions in the planet's circulation pattern. None matched. There was no flare at the time, no disruption in solar wind. No volcanic activity from nearby moons. The only correlating factor was the presence of 3I Atlas, a body whose path and timing matched the zone of ion loss precisely. Then came the second clue. The ESA's JWST probe, positioned on the far side of Jupiter at the time, detected a backscatter of high-energy electrons several minutes after the event. These weren't emitted from the object directly, but they coincided with a realignment in Jupiter's plasma sheet, a vast rotating structure of charged particles encircling the planet. The realignment wasn't large, but it was significant, as if something had briefly interrupted the magnetic flow and then stepped away. Scientists turned to plasma physics for explanations. One theory suggested that 3I Atlas may have temporarily disrupted Jupiter's ion flow by carrying a charged sheath, a type of localized magnetosphere, through the planet's own. This would create a field conflict, like two waves passing through each other, cancelling and reconfiguring in layers. That would explain the proton dip, that would explain the electron rebound, but it wouldn't explain the directionality, because the data didn't just show disruption, it showed extraction. For a period of 7 minutes, a thin filament of excited hydrogen appeared to track the object's motion, not from the object, but from the planet. It looked, to some analysts, like a siphon, a controlled pull. The hydrogen wasn't flowing chaotically, it moved as a focused band converging on the object and then dispersing. It was as if 3I Atlas had opened a gate, momentarily altering the ion distribution of Jupiter's outer envelope and collecting something in the process. This isn't a behaviour associated with comets, it's a behaviour associated with systems. Some researchers hesitated to comment on the record, others suggested parallels with ion drives, propulsion systems that use charged particles to generate thrust. On Earth, we use xenon. But hydrogen, especially in ionized form, is abundant, lightweight, and ideal for electromagnetic acceleration, if you know how to control it. So the question shifted. Was 3I Atlas simply passing through Jupiter's field, or was it harvesting? No alarm sounded, no burst of radio static, no violent reaction, just a quiet, temporary shift in the planet's ion profile, and then silence. Energy moved, directionally. Selectively, cleanly, not taken by force, drawn, with purpose. We've mastered it in theory. We've practiced it with spacecraft for decades. The gravity assist, a maneuver where a spacecraft steals a little momentum from a planet's orbit, slingshots around it, and escapes with more velocity than it arrived. It's a predictable trick, a dance choreographed by Newton and rehearsed by Voyager, Cassini, and countless others. But what 3I Atlas did wasn't predictable. It wasn't a slingshot, it was a shift. In a standard gravity assist, the trajectory is everything. The object must enter at a precise angle, ride the curvature of the planet's motion, and exit along a hyperbolic arc. The laws are strict. Any deviation from that angle, and the energy gain collapses. You leave with less, or with nothing at all. 3I Atlas entered with precision. Yes, but it left at an angle that broke the chart. Let's be specific. The predicted egress vector, based on mass, entry speed, and Jupiter's orbital motion, pointed the object outward along a clean, flared arc, one that would carry it deeper into the solar system or eject it entirely. Instead, after the atmospheric skim, the object departed along a shallower, tighter path. Its outbound trajectory wasn't flung away. It was curved sideways as if a portion of its momentum had been cancelled. It didn't gain speed, it redirected. Telescopes on Earth and orbit began feeding new coordinates into their tracking software. The updates came quickly. Every few hours, the object's vector required correction. It wasn't drifting randomly, it was navigating. The first suspicion was measurement error. Gravitational modelling is complex, especially in Jupiter's magnetic environment. Maybe the equations missed something. But when 3 independent agencies, JPL, ESA's Flight Dynamics team, and the Canada-France-Hawaii Observatory, confirmed identical deflections, doubt turned to recalculation. They plotted the exit vector again, and what emerged stunned even the most conservative analysts. 3I Atlas had left Jupiter's sphere of influence with less kinetic energy than expected, and more precision than should be possible without active correction. This wasn't a loss, it was an exchange. You don't normally give up energy in a gravity assist, you take it, unless you're controlling something else, something internal. A quiet theory began to surface among orbital dynamicists, that 3I Atlas had used Jupiter's mass not for acceleration, but for steering. Not to gain speed, but to change direction with minimal energy expenditure. In other words, it had pulled off a powered flyby. In spacecraft terms, this is the equivalent of firing a small thruster at the right moment during a gravitational swing, not to escape faster, but to pivot. You spend a little energy to change where you're going, not how fast. But 3I Atlas had no visible thrusters, no mass ejection, no jet signature, no torque ripple, nothing that suggested it had spent energy. And yet its path had changed. Deep space radio telescopes tracking the object's microwave emissions noticed something strange during this phase. A dip in its background signature. Not a change in brightness, but in thermal modulation. For 23 minutes, the object's radiative profile flattened, as if internal systems had gone quiet. Then, as the new vector stabilized, the signal returned. A dormant phase, a reset, a maneuver window. In that silence, something changed. Because this wasn't a flyby, it was a correction. Not one caused by Jupiter, but one calibrated using it. The moment it left Jupiter's influence, 3I Atlas changed again. Not in speed, not in trajectory, but in how it looked. For most of its journey, the object had remained dim. It wasn't bright like typical comets that shimmer with sunlit vapor. Its albedo, or surface reflectivity, was well below average. Most believed this was due to a carbon-heavy crust, or perhaps a thickened coma of non-reflective particles. Its appearance had been consistent for weeks, muted, dusky, and oddly stable. But within hours of exiting Jupiter's magnetic wake, something unexpected happened. Its surface brightened. By a factor of 7. The reflectivity spike wasn't subtle, it was immediate and measurable. Ground-based observatories across Chile, Spain, and Hawaii reported it independently. The object's apparent magnitude, the measure of how much sunlight it reflects, jumped rapidly in a 2-hour window. It wasn't a flare, like a sudden ejection. It wasn't a tail event. It was as if the entire body had become more reflective at once. And then it stabilized. This wasn't random. It followed a very specific pattern, one that didn't match solar wind activity or heliocentric distance. The first hypothesis was that some of Jupiter's charged plasma had coated the object, causing a change in surface chemistry, but spectroscopy ruled that out. The surface wasn't coated, it was cleared. Yes, cleared. Spectral analysis from ESA's Infrared Space Observatory showed a sudden decrease in complex organic residue and a rise in crystalline signatures. In simpler terms, the crust of 3I Atlas had shed a dark outer layer, revealing something more reflective underneath. The question was, how? Heat was the next suspect. Jupiter's radiation belts are intense, and a close pass could theoretically heat the surface. But the object's thermal signature had remained stable. There was no evidence of flash vaporization or surface boiling, no tail thickening, no coma expansion, no heat spike, nothing visible that would trigger this type of polish, unless it wasn't heat, unless it was intentional. The spike followed a symmetry, the kind not seen in natural exposure. Brightening happened on the sunward side first, then wrapped across the terminator to the shaded region. This wasn't a random exposure, it was a wave, a controlled sweep. And when analysts overlaid the reflectivity data with magnetometer readings from Jupiter's near field, another pattern emerged. The start of the albedo spike coincided exactly with the final dip in Jupiter's magnetopause. In other words, 3I Atlas waited until it had cleared the outer edge of Jupiter's influence before changing its surface. Why? 2 ideas dominated early models. First, it may have been trying to increase solar efficiency. More reflectivity means more photon interaction. For an artificial construct that could suggest solar charging, data transfer optimization, or thermal equilibrium adjustments. Think of it like reorienting solar panels but on a surface level. Second, and far more intriguing, is the camouflage theory. What if the object intentionally dimmed during its Jupiter approach to reduce detection and interference, then brightened after completing its maneuver? Like a stealth aircraft turning its radar signature back on once it passes hostile territory. But why would it need to hide? More importantly, What needed to see it again? The reflectivity spike wasn't just visible in optical bands, it extended into infrared and polarized light. Even Earth satellites saw the change, especially those designed for missile tracking and solar flare detection. The object had not only become more visible to us, it had also made itself more detectable across a spectrum of frequencies. It was signaling, not with a message, but with presence. I'm still here. I'm not done. Once the brightness spike settled, attention shifted to something stranger, the heat. Every known comet gives off a characteristic thermal signature. As volatile materials vaporize, they release energy. That energy radiates in the infrared spectrum, creating a recognizable heat map across a predictable wavelength band. Ice, dust, and organic residues each emit differently, and their ratios allow scientists to determine not only a comet's composition, but its activity level. But 3I Atlas broke the mold. When infrared telescopes, including NASA's NEOWISE and ESA's Herschel successor array, focused on the newly brightened object, the results came back confused. The wavelength profile didn't match any known class of icy body. In fact, it didn't match any class of natural object at all. The readings were staggered, not blended. Instead of a smooth curve of radiation fading across bands, the thermal signature of 3I Atlas showed stepped emissions, peaks, then sudden drop-offs, then another sharp rise. It looked mechanical, segmental, as if heat wasn't radiating freely from a chaotic surface, but was instead being emitted from distinct panels or zones. Even more disconcerting, the peaks occurred at regular intervals, every 39 seconds. It wasn't visible to the naked eye. But over time, through thermal stacking, the pattern became undeniable. It was as if the object was cycling its infrared emissions, not in response to solar heating, not in tandem with its spin, and not with any detectable gas release. It was artificial, or at least controlled. That realization sent ripples through the observation community. Scientists ran simulations. Was this some kind of pulsed outgassing, an exotic form of sublimation, a fracture cascade? Each idea failed in one key way. None could explain the periodicity. Nature doesn't operate on rigid timers, and comets, chaotic bodies flung across space, don't emit regulated thermal pulses. The implications were sobering. The regular 39-second cycle meant energy was being stored, then discharged. That suggested either internal regulation or external communication, maybe even both, a kind of ping system like a sonar pulse. But instead of sound, it used heat, precise, invisible, infrared heat. What was it pinging? That's when the secondary pattern appeared. Each time 3I Atlas released its infrared pulse, a corresponding microvariation was detected in Jupiter's ionospheric echo. A flutter. Subtle, but present. It wasn't a mirrored signal, more like a whisper bouncing off a wall and returning slightly altered. It was enough. Enough to suggest interaction, not gravitational, not magnetic, but intentional. The pattern suggested a scan, or worse, a handshake, as if 3I Atlas had reached out, left a signal embedded in the space behind it, and was now listening to what came back. And the object didn't just listen, it responded. Following one particularly sharp ionospheric flutter, the next thermal cycle from 3I Atlas came 10 seconds early, just once. A deviation from its rigid 39-second interval. But deviation matters, especially when everything else was so precise. That 10-second jump meant something had changed its behavior, and for a body hurtling through the void, where inertia rules all, behavioral shifts imply awareness, not necessarily consciousness, but system, structure, reaction, and that is not how comets work. What we were seeing, frame by frame, across filtered lenses and layered wavelengths, wasn't the mark of a dying rock evaporating in the sun's heat. It was the mark of a system performing a diagnostic, a heat pattern with purpose, not just to warm, but to listen. It began with a subtle drift. At first it looked like a wobble, an ordinary precession in the rotational axis of 3I Atlas. All spinning objects in space tend to tumble slightly, especially if they're irregular in shape. For a comet-sized body, this isn't just expected, it's guaranteed. But with 3I Atlas, the wobble corrected itself. Over a period of just 16 hours, its rotation not only stabilized but reoriented. And not just in any direction. It aligned almost perfectly with Jupiter's magnetic poles. This wasn't normal. Comets don't correct spin, they react. Outgassing can push them slightly off axis. Tidal forces might cause drift, but controlled, smooth realignment against the background inertia of space, that would require either external torque or internal regulation. Which raised a disturbing possibility. The object wasn't just spinning, it was adjusting, and the direction of that adjustment couldn't be ignored. Jupiter's magnetic field is the most powerful of any planet in the solar system. It's tilted slightly, about 10 degrees, off the planet's axis of rotation, and it stretches millions of kilometers into space, forming a vast, donut-shaped magnetic sheet known as the magnetodisk. Most objects that pass near Jupiter are affected by this field. Dust particles, ionized gases, even spacecraft are gently influenced, nudged, repelled, or captured. But 3I Atlas didn't behave like an object being influenced. It behaved like an object responding, as if it was detecting the magnetic vectors and rotating to match them. That suggested it wasn't passive, it was mapping. Jupiter's magnetic poles aren't static. They drift slightly due to the planet's liquid metallic hydrogen core and internal dynamo effect. But for the most part, they form stable reference points, like invisible lighthouses in the Jovian sky. And now 3I Atlas was pointing toward them, not with its tail, but with its spin axis. That's not how celestial bodies behave, it's how probes behave. The first confirmation came from Juno, NASA's polar orbiter that's been circling Jupiter since 2016. Juno's magnetometers are the most advanced ever sent to the gas giant, and during one of its Peri-Jove passes, the closest approach to Jupiter's cloud tops, it recorded an unusual polarization disturbance, a low-frequency rotation sync. It matched the rotational realignment of 3I Atlas almost exactly. It was like watching two gears mesh, not by force, but by intent, and it didn't stop there. Once the axis stabilized, the object's spin began to accelerate slightly, from 3.2 hours per revolution to 2.95 over the course of just a day. That change was small, barely noticeable on ordinary instruments, but on Juno's gyro-linked magnetometers, the shift was unmistakable. It meant 3I Atlas was spinning not for momentum, but for calibration. It was aligning its own magnetic orientation with the polar field of the planet it was approaching. That's not how any comet has ever acted. It's not how asteroids behave. It's not even how spacecraft behave, unless they're in docking protocols. And if that word sounds absurd, docking, it's only because our frameworks haven't caught up. To dock with something, you need reference points, synchronized rotation, and alignment within a stable field. That's exactly what 3I Atlas appeared to be doing. Not physically, not yet, but magnetically, as if it was laying the groundwork for something deeper, something that didn't involve crashing into Jupiter, but connecting to it. For as long as we've observed comets, one principle has remained consistent. Proximity to the Sun increases activity. As solar radiation intensifies and particles from the solar wind stream outward, a comet's icy surface heats, sublimates, and ejects gases and dust. This forms the familiar halo-like structure we call the coma, a vast envelope of particles that can span tens of thousands of kilometers. But as 3I Atlas drew closer to Jupiter, a reversal happened. Its coma shrank, and not subtly. It began collapsing inward at a rate measurable from Earth-based observatories. At first, astronomers assumed it was a data anomaly, maybe an imaging artifact caused by the brightness of Jupiter or solar interference. But spectrographic analysis confirmed the truth. The outgassing was not just slowing, it was reversing in spatial volume. The coma was compacting, as if being pulled back toward the nucleus. This shouldn't be possible. At its distance from the Sun, still within the heliosphere, still bathed in ample radiation, the coma of 3I Atlas should have continued expanding, or at least maintained its size. Instead, it folded inward, becoming thinner, more coherent, and sharply defined. It wasn't behaving like a cloud, it was behaving like a sheath. The prevailing theories struggle to explain this. In the standard comet model, outgassed particles form a diffuse unbound field. The solar wind pushes ionized gases into a tail, while gravity holds larger dust particles in an elliptical halo. But in the case of 3I Atlas, it was as if some kind of force, internal or external, was actively pulling its atmosphere back toward its core. Even stranger, the structure of the coma began to show radial striations, long linear threads of denser material, spaced at regular intervals. They weren't random, they were evenly distributed, organised. The European Southern Observatory's very large telescope picked up polarization signatures within those threads. Instead of scattering light randomly like a normal coma, the particles within these lines appeared to align in the presence of a magnetic field. That made no sense, unless the coma was magnetically controlled. One suggestion, first proposed in a quiet meeting between planetary scientists and magnetohydrodynamics researchers, was that the entire object was generating a localized magnetic field strong enough to influence the charged particles in its own coma. That would imply internal currents or some form of plasma regulation. Comets don't do that, unless, of course, they're not comets. NASA's Deep Space Network confirmed the anomaly with Doppler-based reflectivity measurements. The material density around 3I Atlas had decreased sharply, but reflectivity stayed the same, which meant the surface wasn't being eroded. It was being shielded. In effect, the coma was no longer acting like a leaking envelope. It was becoming a barrier, a structured interface between the object and its environment. And then, for just 1 hour, everything stopped. The coma collapsed almost entirely. The object was naked, a silent, dense nucleus moving through space with almost no visible atmosphere. And that's when the solar wind did something it shouldn't have. It parted. A measurable gap formed in the flow of solar plasma around the object. Instruments aboard the Solar and Heliospheric Observatory, SOHO, registered a faint drop in charged particle density downstream from the comet, as if 3I Atlas was deflecting the solar wind without a visible tail. That's not supposed to happen. It was, by all known physics, impossible, and yet it happened. Not because the object was hiding, but because it was preparing. Whatever was occurring within that compacted sheath of gas and dust, it was no longer about radiation pressure or passive chemistry. The object was shifting phases again, from reaction to control. Jupiter, the largest planet in our solar system, boasts auroras that dwarf anything seen on Earth. Fueled by the planet's immense magnetic field and its rapid rotation, these shimmering lights at the poles are often triggered by interactions with its moons, particularly Io, whose volcanic activity feeds plasma into Jupiter's magnetosphere. Typically, the auroras react to charged particles funneling along magnetic field lines, creating predictable, cyclic light emissions. But on December 28th, something broke that cycle. Without warning, Jupiter's polar auroras flared, not in response to solar wind, nor to a shift in the planet's internal dynamics, but seemingly in reaction to nothing, at least nothing visible. The Hubble Space Telescope's ultraviolet sensors captured the event in real time. Over a span of 26 minutes, Jupiter's northern aurora ring lit up with a series of concentric pulses. These pulses were not only abnormally symmetric, they were synchronized with a completely different object's trajectory. 3I Atlas. Here's where things took a turn. At the exact moment 3I Atlas passed into a gravitational corridor that brushed Jupiter's outer magnetotail, the auroras flared again, not once, but in a sequence of 3 expanding rings, each delayed by a consistent 6-minute interval. That's not natural behavior. Solar wind doesn't arrive in packets, aurora intensity doesn't normally echo, and certainly, distant cometary bodies do not trigger planetary magnetospheric activity from millions of kilometers away. Unless they do. The Galileo probe's archived data from its 2000 flybys provided a baseline. In all prior auroral storms of that type, the trigger was either solar in origin or came from internal fluctuations within Jupiter's magnetosphere. This new flare-up had no such origin point. Instead, the epicenter of the disturbance appeared, for the first time ever, to drift, as if pulled along a tether that didn't physically exist. At Juno Mission Control, the signal analysis team noticed something even stranger. The spatial geometry of the aurora pulses formed an isosceles triangle, with Jupiter's magnetic north, its moon Ganymede, and the location of 3I Atlas at the time of alignment forming the 3 points. It was like an invisible circuit had just completed itself. But how? Juno's onboard magnetometers provided the next clue. As the spacecraft orbited Jupiter's mid-latitudes, it picked up an extremely faint, yet highly coherent, low-frequency magnetic resonance pattern. It was a form of oscillation too subtle for ordinary detection, but clear enough when viewed through resonance stacking, and it wasn't coming from the Sun or Jupiter itself. It was converging from the same direction 3I Atlas was now approaching. The magnetic field line models were updated, and what they showed didn't match any natural configuration. Instead of curved or twisted field lines flowing normally from Jupiter's poles, one line, and only one, was unnaturally straight. It connected the planet's upper atmosphere directly to a moving point in space. That point was 3I Atlas. Now, auroras are normally the product of charged particles crashing into a planet's upper atmosphere. But in this case, the pattern of the auroral flares indicated something else, a kind of magnetic induction, as if Jupiter's upper ionosphere was reacting to a changing external field rather than an inbound current. This would mean 3I Atlas wasn't sending particles. It was shifting the space around itself in a way that bent Jupiter's field, not violently, but rhythmically, like someone lightly brushing the surface of a drum. To observers on Earth, this might sound minor. To planetary scientists, it was staggering. Because if Jupiter's auroras were reacting to a foreign object's field without particle exchange, that meant the object had a magnetic influence extending millions of kilometers. That influence was structured, coherent, predictable, and it was aimed straight at Jupiter. Jupiter's radiation belts are legendary in both their intensity and complexity. Trapped within the planet's vast magnetosphere, high-energy particles, mostly electrons and ions, whirl at near relativistic speeds, forming toroidal belts that stretch millions of kilometers. These belts are so intense that any unshielded spacecraft passing through them risks critical damage within hours. But beginning on the evening of December 28th, those belts began to fade. At first, the decline was marginal. The Juno spacecraft, equipped with radiation monitors designed to map the particle flux, noted a barely perceptible drop, less than 1%. But over the next 6 hours, that drop turned exponential. By midnight, radiation belt density had fallen by more than 35%. That's not drift. That's erasure. And there was no solar event to blame, no coronal mass ejection, no shockwave, nothing that would warrant a planetary radiation dump of that magnitude. Space weather indicators remained quiet. Earth's own magnetic field showed no sympathetic resonance. In fact, only one vector changed. 3I Atlas. The interstellar object had moved closer, crossing the orbital path of Callisto and nearing the outermost edge of Jupiter's magnetosphere. And curiously, the portion of the radiation belt that began collapsing was not random. It formed a cone, angled directly along the path Atlas had just entered. Visualize it this way. Imagine Jupiter's radiation belt as a thick glowing donut, with the planet at its center. Now, imagine a shadow slowly forming inside the donut, starting from the outer ring, expanding inward, always pointing toward one object. 3I Atlas. This wasn't dispersion. It was convergence, as if the charged particles were being siphoned away, not explosively, not through turbulence, but gently, coherently, quietly, like water drawn into a drain that isn't visible. But here's where the story takes a darker turn. Data from the European Space Agency's JWST mission, currently in dormant mode awaiting its own Jupiter orbit insertion, revealed something anomalous in the outer magnetotail. As JWST coasted through the magnetospheric fringe, it recorded an unexpected dip in particle density. Not a fluctuation, a drop-off. The region ahead of Atlas was becoming a particle vacuum. No known celestial object has ever done this. In known physics, radiation belts can be disrupted by intense solar wind, massive planetary flares, or magnetospheric collapse. But there were no shock fronts, no irregularities, no signs of any emissions coming from Atlas at all. And yet the belts were vanishing. So what could do that? One theory quietly circulated among plasma physicists: magnetic absorption via an artificially modulated null field. In simpler terms, the space around Atlas wasn't just neutral, it was actively cancelling charged particle motion. This requires more than mass, it requires intention. And before the theory could be dismissed as science fiction, Juno's magnetic flux sensors picked up another wrinkle, a harmonic dampening signal. This was a form of magnetic silence, a specific frequency cancellation pattern that neutralized particle acceleration within a confined zone. Again, the pattern matched the path of 3I Atlas. It's as if the object wasn't simply moving through space, but pulling a bubble of nullified physics with it, a kind of anti-field, one that devoured radiation as if it were matter, not chaotically, systematically. And all of it pointed to one conclusion. The object wasn't merely passing by Jupiter, it was preparing. Preparing for an interaction, perhaps a descent, perhaps something else. But in either case, it was terraforming the magnetic environment in advance, clearing the noise, stabilizing the medium, or worse, feeding. For decades, scientists viewed radiation belts as an obstacle to exploration. Now they might have been the appetizer for something we still couldn't see clearly, and Jupiter, the great magnetic fortress of our solar system, was no longer immune. Io is not a quiet moon. It's the most volcanically active body in the solar system. With over 400 active volcanoes, massive sulfur plumes, and a tortured surface reshaped every few years, Io is Jupiter's screaming child, a moon in constant geological rebellion. Its core is molten, its crust fractured, and its orbit trapped in a tug-of-war with Jupiter's gravity and the nearby moons, Europa and Ganymede. Tidal forces stretch and squeeze it like putty, generating internal heat that powers its explosive outbursts. So when a new tremor is detected on Io, no one panics, at least not immediately. But this time was different. On the morning of December 29th, seismographic readings from the Galileo Seismic Array, an artificial sensor grid deployed across Io's equator decades ago, picked up a wavefront. Not a subsurface tremor, not a tectonic fracture, but a shock wave. And it was coming from above. This was a different kind of signal, sharper, more coherent, more directional. It passed through the crust like a scalpel, not a hammer. The waveform matched nothing in the catalogue of volcanic precursors or impact triggers. There was no plume, no quaking, no surface uplift, just a wave, clean, pulsing, and perfectly timed. It lasted only 6 seconds, but the implications reverberated far longer. Initially, scientists suspected a micro-impact. Perhaps a small asteroid fragment had pierced Io's thin exosphere and delivered a glancing blow. But orbital imagery from ESA's JWST flyby later confirmed no such crater or ejecta trail. The surface remained untouched, and more curiously, the pulse originated beneath the sensor grid, but had no matching internal precursor. It was as if the wave had passed through Io like an ultrasound. Not from within, but from an external origin that shaped the moon's crust like an echo chamber. That's when the trajectory analysts noticed something deeply unsettling. The pulse trajectory pointed directly back to a single moving body in space, 3I Atlas. It wasn't nearby. In fact, it was still over 1.3 million kilometers from Io at the time. But the angle was precise, and the delay between Atlas's closest pass to Jupiter's magnetic equator and the arrival of the shockwave on Io was consistent with an external signal, one travelling not at the speed of sound, but as a form of magnetosonic resonance. In other words, it wasn't a mechanical wave, it was a magnetically modulated energy burst, possibly encoded. Jupiter's magnetosphere, vast and deeply conductive, could have served as a transmission medium. The idea is unprecedented in planetary science, but not in radio engineering. On Earth, we use ionospheric layers to bounce signals around the planet. On Jupiter, Atlas may have used the entire radiation belt as an amplifier, and Io, orbiting within that field, became the receiver. Except Io has no antennas, or maybe it didn't need one. The moon's iron-rich core, threaded by electromagnetic friction, could resonate like a tuning fork if struck by a field pulse of the right geometry. That's exactly what the data suggested. And to make matters more complex, similar but weaker, pulses were later detected on Europa and Ganymede, but not simultaneously. Each moon received its own burst, as if in sequence. A signal cascade, a triad. Someone, or something, was scanning, and it was using Jupiter's own moons as test subjects. Perhaps the strangest part wasn't that this could happen, it was that nothing, absolutely nothing, in our entire catalogue of natural phenomena could explain it. Io wasn't erupting. It was responding, and 3I Atlas was listening. Temperature spikes on Jupiter aren't rare. This is a gas giant with a surface pressure over 100 times that of Earth's, a layered atmosphere composed of molecular hydrogen and helium, and a chaotic weather system that dwarfs anything we've ever experienced. Its Great Red Spot alone has raged for over 3 centuries, with winds moving at over 430 kilometers per hour. Lightning storms the size of continents tear through the clouds, driven by complex convection and supercharged vertical turbulence. But what was detected on the afternoon of January 1st wasn't any of that. It wasn't a superstorm, it wasn't auroral heating from the magnetosphere, and it wasn't tied to any solar event. Instead, what NASA's Juno spacecraft detected was something entirely different. A localized thermal anomaly in the lower atmosphere of Jupiter, one that came and went without triggering an upper atmospheric disturbance. It was as if someone had lit a match in the deepest layer of a 1,000-kilometer thick gas blanket, and then snuffed it out before the flame could rise. The detection wasn't even meant to happen. Juno was on a peregrove maneuver orbiting low across Jupiter's southern hemisphere, performing routine microwave radiometry. Its mission was to map water content deep beneath the clouds. But during Pass 57, its MWR, microwave radiometer array, pinged back something that made the operations team at JPL pause. A sharp, narrow-band thermal increase centered at latitude -11 degrees, longitude 83 west, a region with no known convective hotspots, no active storm cells, and no magnetic flux deviations. It lasted 36 seconds. Then it was gone. Initially, scientists assumed a sensor glitch, but secondary instruments aboard Juno confirmed it. The radiometer wasn't the only system to pick it up. Gyrum, the Jovian infrared auroral mapper, detected a spike in infrared brightness in the same coordinates, with thermal signatures reaching over 980 Kelvin in the deep troposphere. That may not sound extreme by Earth standards, but on Jupiter, at that depth, it represents an injection of energy 12 times higher than baseline. It was like turning on a localized furnace, deep in a pressure zone where solar energy barely penetrates. And here's where it got stranger. There was no vertical plume, no buoyancy lift. No ripple effect in surrounding zones. It was as if the heat had entered laterally, not from below or above, but across. That's physically impossible under normal planetary thermodynamics. Jupiter's interior is hot, yes, but its heat rises gradually through convection. It doesn't inject itself sideways, and certainly not in perfectly bounded square-kilometer patches, unless something injected that energy from the outside. When the data was forwarded to the Deep Space Climate Observatory, DSCO-VR team for cross-analysis, the pattern became clearer. At the exact moment of the spike, time-stamped to 1406 UTC, the inbound trajectory of 3I Atlas had placed it directly in line with the lower Jovian magnetic corridor, a corridor that connects outer orbital space to the deeper, denser atmospheric layers through invisible flux tubes, channels of magnetic conductivity that normally only shuttle plasma and field-aligned electrons. But on this occasion, something else had passed through. NASA's plasma wave subsystem, retroactively reviewing signal interference during the same window, detected a pulse, short, focused, and perfectly aligned with the region of the heat bloom. A signal or a strike? If it was a strike, it left no chemical residue, no ammonia anomaly, no hydrazine fingerprint, nothing to indicate combustion or kinetic impact. Whatever it was, it injected pure energy, controlled, focused, intentional. It was, by every metric, a targeted thermal event. This introduced a terrifying new framework that 3I Atlas may not be observing. It may be testing. Testing what? Conductivity, response latency, thermal dissipation thresholds, atmospheric modulation. It was as if Jupiter, the largest and most extreme laboratory in the solar system, had become part of a larger experiment, one we didn't initiate. A few days later, data from the ESA's JWST probe confirmed a corollary anomaly. Minor changes in the refractive index of Jupiter's lower cloud deck, specifically in the same region that had experienced the spike. That's not just heat. That's structural modulation, a change in how light moves through gas. Think of it like tapping on the side of a balloon and watching how the skin flexes, not randomly, but in a pattern. And then, just as suddenly as it appeared, it was over. The anomaly dissipated, temperatures normalized, the field stabilized, no permanent scars, but the implications remained. This wasn't a random flare. It was surgical. And it had precision we didn't even think was possible in a gas giant. From over 2 million kilometers away, 3I Atlas had, apparently, interacted with Jupiter's lower atmosphere without entering it, without touching it, and without being seen. The scientific papers rushed to use cautious language: possible magnetic coupling, potential resonance heating, unexplained thermal gradient. But the underlying tension in the academic community was clear. This wasn't theory anymore, it was data. 3I Atlas had shown the ability to inject energy remotely, target specific coordinates, and vanish without trace. And if it could do that on Jupiter, what happens if it ever turns toward Earth? As the collision began to take shape, the first truly global effect was not visual. It was magnetic. The magnetosphere, Earth's invisible shield, is not just a defensive layer. It's an interactive membrane sensitive to solar wind, solar flares, and every cosmic tremor that echoes across the heliosphere. And on the morning of January 1st, a shock pulse entered that system unlike anything recorded in modern geophysics. It did not arrive from the Sun. It came sideways, from the distant flank of Jupiter, where 3I Atlas had just made contact. It was not a jolt, it was a wave, a slow-building, system-wide compression that pressed inward on the magnetosphere like a balloon being squeezed in water. Magnetometer readings across Earth's orbit, from the GOES satellites to instruments aboard lunar orbiters, all showed the same anomaly: an asymmetric distortion in the magnetotail, delayed by precisely the amount of time it would take a subluminal pulse to travel from Jupiter to Earth's magnetic field. But here's what changed the conversation. The shock front behaved as if it had structure. Not noise, not static, but a resonance pattern, low frequency, sustained, and repeating in a triplet cadence. This wasn't something emitted randomly. It was something that appeared designed to reverberate through the magnetosphere without immediately collapsing it. In other words, it was calibrated. This was not theoretical anymore. Across observatories, the wording in internal documents shifted. They no longer used impact echo or radiative coupling. They used a new term, magnetoform signature, a coined phrase meant to describe an interaction that doesn't simply trigger Earth's magnetic field, but reshapes how it functions. At ground level, the effects weren't immediately catastrophic, but they were measurable. GPS fluctuations increased. Auroral arcs shifted several degrees lower in latitude. Pilots flying high-altitude transpolar routes reported strange instrumentation behavior, not failures, but phase lags in signal syncing, as if the satellites overhead were subtly desynchronized from the ground stations below. One of the most compelling observations came from the upper ionosphere. There, arrays like HARP and SuperDARN picked up ripples in ion density that didn't align with any known atmospheric tide or solar wind model. These ripples moved in unison with the frequency of the magnetoform signature, building, collapsing, and rebuilding in a pattern that mirrored the theoretical wavefront caused by a high-mass object perturbing space near Jupiter. What was so striking was the restraint of the effect. This wasn't an energy dump, it wasn't a flare or burst. It was a signal, modulated, structured, and non-destructive, as if designed to test Earth's electromagnetic profile, not shatter it. And that raised another question. Why would a collision near Jupiter create a magnetoform pulse aimed at Earth? Astrophysicists began re-examining old data from past solar system events, including comet Shoemaker-Levy 9's dramatic collision with Jupiter decades earlier. But nothing came close to this level of indirect magnetic influence. That collision had produced light, heat, and debris. This one produced structure, meaning, design. The data pointed to a hypothesis that made many scientists uncomfortable. The collision had not been an endpoint. It had been a switch, triggering a cascade not just of particles but of instructions embedded in the field lines themselves. A collision that rewrites field structure, not by force but by function. In a moment where everyone expected a shockwave, we received a symphony, a low, repeating note that stretched across millions of kilometers and gently altered the envelope of our planet's protective shell. And in that calm, resonant distortion, Earth itself had become part of the conversation. While Earth absorbed the silent ripple through its magnetosphere, attention turned sharply back to the origin point: Jupiter. Initially, the gas giant had acted as the impact host, a buffer, a massive planetary sponge that absorbed the kinetic arrival of 3I Atlas. But within hours of that supposed collision, something began to change, not with Atlas, but with Jupiter itself. It began subtly. The outermost bands, those familiar belts of tan, rust and ochre, which had swirled for centuries in stable rotation, began to lose their symmetry. The rotation didn't stop, it warped. Planetary scientists watching the time-lapse footage from JunoCam noted that the belts were no longer moving in parallel. Instead, they were twisting into irregular gyres, like a sheet of cloth being wrung slowly by invisible hands. This wasn't turbulence, it was something else. Jupiter's great red spot, the most enduring storm in our solar system, showed the first evidence of this anomaly. It didn't fade, it accelerated. Its internal counter-rotation reached a speed 17% higher than its average velocity in the last decade, but it also began to tilt, not just in the direction of spin, but on its axis, leaning, as if caught in an external current or under the influence of gravitational torsion. Across observatories, models failed. Simulations meant to anticipate the rotational behavior of Jovian bands broke down within 3 cycles. The parameters no longer held. The bands were not responding to standard meteorological patterns, not to solar wind, not to inner convection. They were responding to something introduced during the moment of contact, something that wasn't there before, and that's when the thermal data began arriving. The European Space Agency's JWST probe, observing from a Lagrange point, reported a slight but consistent rise in infrared emissions from Jupiter's mid-troposphere. Not from its core, not from its magnetosphere, from the cloud bands themselves. It was as if the bands were heating, not uniformly but in pulses. Each thermal flare aligned not with solar input, but with the trailing arc of 3I Atlas's previous motion. This implied energy had been deposited or injected into the system, not by heat transfer, but by some other, more intricate interaction. Something that either seeded resonance within Jupiter's atmosphere or reprogrammed the electromagnetic pathways that control its winds. The language in the scientific community once again had to shift. No longer were they speaking in terms of storm behavior or rotational variance. The new term proposed by a working group at the Lunar and Planetary Institute was atmospheric dissolution. It did not mean that Jupiter's clouds were vanishing. It meant that their behavioral cohesion was unraveling. The planetary memory that had kept storms locked in place for centuries was eroding, replaced by a more fluid, unstable, almost programmable turbulence. One chilling hypothesis suggested that the impact of 3I Atlas had left behind not debris, but instructions, injected into the fabric of the Jovian atmosphere. Instructions that overrode natural formation, instructions that could manipulate planetary weather not through force, but through design. Jupiter, the great stabilizer of our outer solar system, was becoming the testbed for a new kind of alteration, not terraforming, but atmoscripting, the possibility that clouds, storms and heat could be shaped by external, possibly artificial influence. And if that was true, if the gas giant was now responding to something that no longer obeyed gravity alone, then Jupiter wasn't just a shield anymore. It was a transmitter, a modulator. The bands we once studied for beauty and chaos were now broadcasting something back, not just to Atlas, but perhaps across the entire system. And Earth, once again, was within reach of that signal. As Jupiter's bands dissolved into programmable turbulence, Earth's instruments began to detect something unexpected, a feedback loop. What started as subtle changes in the Jovian atmosphere now seemed to have a mirror on Earth's side of the solar system. It began with magnetometer readings from low Earth orbit satellites, which showed irregular flux patterns not tied to solar weather. These fluxes came at intervals, not constant, not chaotic, but rhythmic. A cycle, one that echoed with precise delays tied to Jupiter's rotation. The signal, or whatever residue of energy Atlas had embedded in Jupiter, was bouncing, not in a physical sense. There was no matter moving back and forth, but the magnetic signature, the waveform, began showing up in our ionosphere, the same periodicity, the same pulse interval, 47 minutes, the same timing that had followed Atlas before its trajectory shifted. Only now the signature was stronger. Radio telescopes operating across the Very Large Array in New Mexico began to report interference. not from Earth-based sources, but from low-frequency distortions coming not from deep space, but from within the Earth-Moon system. At first, it was dismissed as solar reflection, but solar activity had been quiet. The sun wasn't the cause. By December 31st, an emergency coordination protocol was activated. Instruments across continents, in Hawaii, Chile, South Africa and Australia, began logging the same readings, a repeating pulse, modulated in frequency, but identical in amplitude. It wasn't loud, it wasn't weaponized, it was subtle, but it was real, and more importantly, it was targeted. The pulse shifted ever so slightly in orientation with each Earth rotation. It was tracking something, not a fixed point in space, but a moving one, something on Earth's surface. This changed everything, because it suggested that whatever 3I Atlas had done inside Jupiter, it had not just altered the gas giant, it had initiated a process that could now respond to changes on Earth. Not autonomously, but as if in observation. The ESA's Sentinel-6 satellite logged atmospheric scattering events in the upper troposphere, occurring at the same 47-minute intervals. These weren't meteorological events. They weren't caused by wind shear or cloud pressure. Instead, they looked like localized disturbances, thermal diffractions, in layers of air typically immune to such rapid changes. The shapes were consistent, symmetrical arcs, as if something was creating geometric imprints in the sky itself. Ground-based telescopes began pointing toward Jupiter, trying to find any visual cause. But by this time, Atlas was no longer visible. It had moved. Infrared observations from the Spitzer Space Telescope's archive suggested a departure path, not back into space, but into the planet. A descent. A sinking, slow and deliberate. No flare. No heat spike. Just a gradual vanishing into Jupiter's deeper clouds, like it had parked itself there, as if to hide, or perhaps to merge. And that raised the deepest question yet. If Atlas was no longer behaving like a natural object, if it had initiated a change in Jupiter that could now send signals back to Earth, adjusted and modulated through one of the most complex atmospheric systems in the solar system, then this wasn't just an interstellar visitor, it was a relay, one that used planets, magnetic fields, atmospheric lenses and rotational timing to create a system, a network, capable of watching, adjusting, and maybe even shaping. And if we were receiving the echo of that system now, what came next might not be observation, it might be response. So now we're left with a question that none of our instruments can answer. Not how fast 3I Atlas moved, not how it altered Jupiter's magnetic shell, not even how its tail flipped, ignited or disappeared. Those were all observations, data points, events we could see, plot and compare. But the question that remains is about intent, because somewhere beneath the roiling clouds of Jupiter, something may still be active, something that wasn't destroyed, but deployed. Not a comet anymore, not even a structure, but a presence, one that uses plasma instead of propulsion, one that bends atmospheres instead of orbit paths, one that didn't just pass through our system, but acted within it. And if Earth is now part of that system, if these pulses are indeed tracing our atmosphere, sinking to our rotation, embedding into our magnetosphere, then we are no longer observers, we are part of the equation. We're not just looking outward anymore, something out there is looking back, and whatever it is, it may have just begun. So stay curious, stay alert, and keep your eyes on the signals, because the story of 3I Atlas is still unfolding. I'll see you at the next anomaly.